Alright, what I'm going to show you in this video is basically how to take a two-dimensional STL file and run a static elasticity analysis on it. So we can maximize this window by just getting rid of the command window altogether and minimizing the workspace as much as possible, so we can see this pane here. So just to refresh, we have a domain, 2D domain here, where we can apply a certain boundary condition, Dirichlet boundary condition, and a Neumann boundary condition. That is basically a fixture, and this is basically a load. We have a traction force here, and we have some normal direction here. So the partial differential equation looks like this. This is what we assume. So it's a static equation, and we have basic Hooke's law, where we have these two parameters here, which are the Lamé coefficients, which we can select which type of theory we want to use, if it's a plane strain or plane stress. And then we have the Neumann boundary condition here and the Dirichlet boundary condition here. So our problem looks like this. We have basically we have a bracket. We can mesh it, so we can create a mesh with a certain number of elements, and these are linear triangles. We will only be focusing on linear triangles. We have a distributed load on the upper part of this. We have locked these nodes in both the X and Y directions. And we have this region here, we have locked only in the X direction. So the reasoning behind this is that, so this area here is somehow attached to a wall by some sort of screw or somehow adheres to it. So it cannot move in the Y or X direction. And this here is just resting at the wall basically, so it cannot go in the X direction. It cannot go either in the negative X direction or the positive X direction, but we don't expect this to go in the positive X direction. So this model works for assuming that this is just resting against the wall. Right. So if you watch my previous video tutorial, you will see that this thing has actually been topology optimized using SolidWorks or Fusion 360. And then we drew this on top of our initial design. We drew pockets, which we cut away, and this was the result. Now we want to check if the stresses in here are underneath the yield stress, because the topology optimization does not give us that. So we still have to check the structural mechanics of our design. So we're asking ourselves, given the material parameters and the boundary conditions, what is the maximum stress? Is there any fixture stress? What does that mean? Well, basically it means, is there any stress that is induced by the boundary conditions that is not there in reality? And are there any stress concentrations? If you have sharp corners, we have stress concentrations, and those are usually fixtures as well. And if we refine the mesh, they just tend towards infinity. So we will get, in reality, we will get plastic deformation there, which of course reduces our stress. But assuming linear elasticity, we get very high stress at those regions. And they're typically of interest because we want to avoid these by changing the design. So what type of stress is highest is also another thing we want to know. Typically, we calculate the von Mises stress, but we are also interested in principal stress. Principal stress will give us the information if certain areas of this bracket are in tension or compression, and we want to calculate that, we want to visualize that, and we want to draw conclusions from that. Finally, we can answer the question, is this a good design? And we can have an opinion on that based on the fact of the analysis. basically we can have an opinion about the boundary conditions and the stresses induced by them. We can have opinions about stress concentrations, and we can give design ideas of how to change this design. And basically, if you have this tool now, you can actually go to your CAD software, change the design of this, and then run this again in order to iterate. So yeah, that's the idea of the workflow anyway. On the exam, you will probably not be able to do that because of time limitation. So you're just going to run your study and analyze the bracket or whatever design you get to analyze, and you will answer these same questions. So the solution is to use this static elasticity, static 2D elasticity.m file. And if you take a look at that quickly here, you can see that I haven't really gone through the trouble of documenting this perfectly. But that's why you will see this. That's why you're probably watching this tutorial to understand how this works. And it's a complete solver. The stuff we haven't really talked about is mostly in here in elasticity 2D. So I've sort of showed this. So this is actually created so we can run a second order parametric element here as well. But yeah. So what we haven't talked about in the course is how to do the finite element method for solving the elasticity problem, and this is very similar to how to solve the heat equation. It's just that we're dealing with 2 degrees of freedom per element per node. That's why we need to handle this in a different way, and it becomes a little bit complicated. But yeah, and also the assembly routine here is made such that this thing runs much faster. You don't need to know anything about this. You don't even need to open this. We will only focus on how to use this to get a solution. So this still utilizes the PD toolbox, so we need to have that installed because we will generate this graph here. It will basically read in the STL file, and it will identify certain regions that we will use to apply boundary conditions. That's what we need to do. That makes life a lot easy. Also, it's also a mesher built in, so we will use it to create our mesh. Make sure that you have the toolbox installed. If you're on a school computer, you most definitely have that, so you don't need to check it. For this particular file, make sure that it is in your working folder. You can check what your working folder is up here. This will tell you the working folder, and this here will tell you the file location of this file. And make sure that this static 2D elasticity.m file is in your current folder. Otherwise, this will not be able to run. These two files, the static elasticity 2D MLX file, can be in a different folder, but your working folder must be where this file is located in. If you don't have that in the working folder, make sure to read this error text. It will scream at you and tell you that there's an error and you need to have that file in your path or in your working folder. The geometry is being loaded by a certain file, an STL file. In this case, this STL file is called bracket.stl. On the exam, you'll probably get something else here, so you insert that, and everything else is being kept the same, and it will generate this figure for you here, where you can see your geometry and these region numbers here, the edges here. Next, we can create a mesh from this geometry. So we have a mesh size here by this variable h, which we set to 10 millimeters in this case. So this is where you just change this thing here. You don't need to care about changing the mean or max or the h grad or the geometric order. We will keep things linear. You could change this to quadratic and this method will still work. It's just that everything will become more accurate, and then you would need to change your method of computing the stresses, and we will just skip that altogether and just focus on linear. If you're interested in understanding how that works and you want to implement that during the course, be my guest. I will help you. I will gladly help you to do that. So just ask me, how do you do this for quadratic if you want. But on the exam, we will just run it with linear. All right, you can read this text here. It's I provide detailed information of what everything does. You don't really need to understand that though. So you just need to do whatever I did here and it will run. The mesh is visualized by PDE mesh, and we will get this picture here. So you get a visual feedback on how the mesh looks like, and if you need to increase it in order to, resolve your stress later on. Next, we have material parameters and the 2D simplification. So this thing is plastic, so we have a quite low elasticity modulus here, and the thickness is quite thick by 8 millimeters. And we're assuming plane stress. So we have a thin object. We don't have an infinite thickness or a very high thickness. That would be plane strain. Plane stress, that means lambda and mu is the following. You can check this in your notes. You should be able to figure it out given the thickness. So if you have something that is supposed to be very thick, usually it's plane strain. But yeah, so this is a big assumption that you're making, and be sure to understand what the implications of this are. Also, I expect you to discuss this if you want to get full credit on this particular problem. So once you've done that, we choose a body load, and in this case this is just 0, but it needs to be inserted because the static 2D elasticity requires a body load. So this is just set to 0 because there is no body load on this. A body load would be something like gravity. Right. You can check what the output of this is. So you will, in particular, you will see here that you get a stiffness matrix. So this is what is generated, and you have a load vector. This load vector here will contain the loads that are given in the body load. And since this is 0, this is just going to be a 0 load vector. Note also that there are no prescribed displacements yet because we didn't set them, and there's no prescribed degrees of freedom because, again, we didn't set them. So that will be done later. In the next step, we will set the load boundary condition, and that will be done using the compute surface load method. So a method is basically, because this is object oriented, this thing here is a class and it generates an object, and this object is what we are working with. So this same object here has a method, which is the compute surface load, and it's just used like this. You don't need to care about what it is, how it works. You just need to understand that this stuff here does something, and I will tell you what. So it requires a region. So you set a region by looking up here. Which region do we want to set this surface load to? We can check our problem all the way up here, and we see that, okay, on this region here, so on top, there is a load. And then we check what region this is, and this is region 6. So that means, scroll down, at region 6, we have a force, and this force has a magnitude of 200 in this direction here. And the load is given, supposedly. Is it not? Yeah, it says here, the load is 200. So you can check that from the picture. So the direction and this visualize parameter here says just that we will generate a visualization of this. So you get these arrows pointing downwards, so you can see that you're doing it correctly. Also, it will spit out this force vector, and if you take the sum of this force vector, you're expected to get back to 100. And in fact, if you do that, we get negative 200 here because it's in the negative direction of the y component. So that's the force. You can add more forces to this, to other regions if you want, if that is required. So you just do that stuff again. You just copy and paste this and then add another force to another region if it is required. Next we have fixtures, or a Dirichlet boundary condition. Region 4 and 3, if you check the regions up here, I can see that. We have region 4 and 3. So in region 4, we're supposed to lock the displacements in both x and y, and at region 3, we expect to lock them only in region, only in the x component here. So we do that by applying this this prescribed displacement method twice. So once for region 4 here in the x and y direction, and once for the for region 3 only in the x direction. And that's it. That's all we need to do, and then we just solve the system by running u is equal to stat.elast.solve, and it will solve it for us. And u is now a vector that is populated with a bunch of values, and it is on this way here. It's called the void notation. So we need to split that up so that we get a matrix where the first column is the x component and the second column is the y component, and we do that by this command here. And once this is done, then we can compute the magnitude of it, by Pythagoras theorem. It's just that we do it per element using this dot here. So we take the first column and we square that using the dot square operator. So every component here is squared. If we omit this dot, then it's basically like doing this vector times itself, and it will fail because you cannot do that operation on a vector because it's not transposed correctly. So yeah, that's why this is needed here, this dot. So yeah, the components in the first column squared plus the components in the second column squared, and the square root out of that will yield a new vector which contains the magnitude of the displacements. And we can check what the maximum is by doing max on this vector. We can see here that the maximum is 0.4 basically millimeters, which is reasonable, right, for this bracket, which is 200 millimeters wide and 100 millimeters thick, and we apply 20 kilos on top of it, and it is plastic material. Now we up the scale because otherwise we wouldn't really see any different deformations, and we visualize this stuff. So this visualization routine is made transparent here for your sake, so you can see how to actually code this. I could have just created a function, but I want you to understand how this works. So we first need the nodes, which are the connectivities. It looks like this. So basically this means that if you read it from top to bottom here, the first element has a node 175 and 66 and 125, and these nodes are referencing these points here. So the points are referenced by these triangles. So every row here is basically one element or one triangle with 3 nodes, and the nodes numbers are whatever it says there. These two variables are used to plot this, to create this figure here, which you can see on the side. So we write figure to create a new figure, set the axis equal here, so you can. So this thing is actually the aspect ratio of this is correct, so it's not stretched out. And then we run the patch function, and we set faces to nodes and vertices to what? Well, P is the original bracket, and then we add the displacements to it, and we scale them up because they're really small, right? Really small, so we wouldn't see them really. So we scale them by a factor of 50, and this is just arbitrary, so you can play around with this until you feel comfortable with whatever you're getting. The face color is set to interpolate, so it's going to interpolate between here, so you will get something that is gradually. It's not going to be one color per element, but a varying color range. And the C data, its color data, is set to UR, so it's basically one color per node. And that's why we can use the face color interpolate, because it will interpolate the colors in the nodes to the faces. And the most important thing we need to do here is set the color bar. So just write color bar, it will generate a color bar for us. Otherwise we have no idea what these colors mean. So that's the most basic visualization we can do here. And if we want, we can actually add to this. We can say that the edge color is none. So if you run this by pressing F5, we get a nice figure without the mesh. But if we want the mesh, but we just want it to be a little bit less intrusive, we can do alpha or edge alpha, and we can set this to some low value like 0.2. That means that the transparency of the edges will be low. So it sort of shines through, but weakly. So we can see the mesh, but it's not disturbing us too much. So we can still see the color grade of this. And just to make something that is a little bit more descriptive, we can add a title to this, and this string will be composed of a string and this scale here. So you can write something like this: displacement field, or you can do magnitude of the displacements, and then scale equals, or scale colon, space, and then comma. We will add a new string to this, which is num to string, and then the scale number. So that it will convert this number to a string, and it will append it to the side here. So if you run this, you can see that it says magnitude of the displacements, scale is 50. So this is 50 times enlarged. So it's a nice descriptive title here. Yeah, one more thing I can show you really is that you can go up here and you can change the size of these elements to 5 millimeters. And if you run this using F5, you get a much finer mesh, and everything just still works out the same, and you have a finer mesh here, which of course means that your stresses will be finer later when you run this. In the next video, we will actually see how to compute the stresses from these displacements. All right, good.